In this lesson, we're going to continue our conversation with airflow and ductworks, and it's pretty important if you're coming into this midstream, please go back and watch units 1 through 3 first, okay, because these do build up, okay? Each unit builds upon the prior unit, so it's pretty important you watch these in the lesson. As I've mentioned before, these slides are adapted from a book called Airflow and Ductwork by Leo A. Meyer. He sells his books through Llama Books, llama-books.com. Okay, and it's pretty important that if you want to know more about this than these PowerPoints go through, if you want more examples, please grab his book. Okay, it's actually a pretty good book. So in this lesson, we're going to be talking about pressures in ductwork. Okay, so far we've talked about the basic components. We've talked about some measurements, the area, okay, for round and rectangular duct. We've talked about airflow in terms of air volume and speed. Okay, now we're going to be talking about pressures. Okay, it's pretty important to understand there's 3 pressures in a duct. Okay, and they're all related to each other. We have static pressure, sometimes shown as SP. We have velocity pressure as VP, and we have total pressure as TP. Okay, so we're then going to also talk about the 2 causes of pressure loss in ductwork. Okay, we have friction loss and dynamic loss. So let's first talk a little bit about atmospheric pressure. Okay, we have a pressure at sea level. Okay, that's basic atmospheric pressure. Okay, then we have up into the mountains closer to 5,000 feet, has a different pressure. So atmospheric pressure is the weight of the air above us. Okay, how much weight does the air have? And yes, air has weight. Okay, air weighs 14.7 psi at sea level. So if you're working in a state such as Florida, which is almost at sea level or just slightly above, your atmospheric pressure is going to be 14.7 psi. Okay? Now, as you go to higher elevations, the atmospheric pressure becomes less and less as you go up because there's less air above you. So the weight of the air at 5,000 feet above sea level is only 12.25 psi. Okay, so again, as you go up, the atmospheric pressure changes. Okay, now we have a thing called positive duct pressure. Okay, this is pressure above atmospheric pressure. So consider our 14.7 zero. If you're on the supply duct or the outlet side of the fan, it's going to be a positive pressure. That's going to be above atmospheric pressure. We also have negative duct pressure. Negative duct pressure is in the return air of the duct. Okay, negative duct pressure is going to be below atmospheric pressure. Okay, it's going to be on the side of the blower that is pulling into the system. That is negative duct pressure on the return side. So positive duct pressure is always in ductwork on the supply side of the blower, the side that's pushing air towards the conditioned space. Negative duct pressure is on the return side of the system, the side that is pulling air from the space. Sort of makes sense. Okay, it's below atmospheric pressure. So when we take a look at a piece of ductwork, okay, we have a lot going on in terms of pressures. Okay, I have atmospheric pressure as long as there's no blower on it. I have atmospheric pressure on the outside. I have atmospheric pressure on the inside. I have atmospheric pressure all around it. Now, I stick a blower onto this. I am now pushing air into the ductwork from the blower, and that higher pressure causes the air to flow. Okay, because at the end of the ductwork, we have low atmospheric pressure, or air that's at atmospheric pressure. Okay, air will always flow from an area of greater pressure to an area of lower pressure, so that air coming out of the fan into the supply duct is at high pressure, and it's going to spill out or flow into the surrounding air. Think about a water hose. Okay, turn the faucet on, put your finger over the end of the water hose. The pressure in the water hose is great. It's pushing out from around your finger onto your lawn, which has no pressure. Okay, water and air are very similar. They will always move from an area of high pressure to an area of low pressure. So let's talk about one of our first measurements of air pressure, static pressure. The static pressure is what keeps a balloon inflated. Okay, you'll notice the arrows in here. They're pushing outwards against the shell of the balloon in all directions. Okay, that is static pressure. In ductwork, once I have air being moved through the duct, I have static pressure. It is the pressure that is pushing outwards against the side of the duct. Okay, let's go back to our balloon. Velocity pressure, if I untie the end of the balloon, okay, the air that's streaming out is velocity pressure. It's what will make a balloon shoot across a room. Okay, the balloon reacts to the velocity pressure. Velocity pressure is the pressure that is being caused by the air moving. Okay, so I have velocity pressure and I have static pressure. Add the two together, that's my total pressure. So in a piece of ductwork, okay, or in an air conditioning system, the static pressure is the air being pushed out or pulled in against or from the outside of the ductwork. The velocity pressure is the pressure of the air moving. Two different pressures, two different tools we use to measure. My total pressure is the static and the velocity pressure. Now, friction loss is caused by the air rubbing against the side of the ductwork. Friction, okay? Any part rubbing against another part causes friction. Friction causes a loss of static pressure. Okay? So let's take the ductwork, okay, from A to B. Okay? If you look at the chart here, my velocity pressure, okay, is the blue at the bottom. My velocity pressure, as long as the air retains the same velocity as it moves through the ductwork, in other words, speed, my velocity pressure is going to stay the same. As the air moves through the ductwork, my static pressure, okay, is going to decrease because of the friction against the side of the duct. And different duct materials has different levels of friction. So we have velocity pressure and static pressure is total pressure. And you'll see that now friction loss offsets the static pressure. So where point A is, where I have high static pressure and high velocity pressure, as I move down the duct further away from the blower, my friction loss increases, my static pressure goes down, and my velocity pressure remains constant. Because I haven't changed the speed of the air, I'm just decreasing pressures. Why is this important? Okay, because we have, as you go down the ductwork further and further away from the air handler, you're going to have lower pressures of air to work with. And this is part of duct construction. Okay, so if I take a pressure reading at the air handler, it's going to be much higher than the pressure reading at the outlet register or at a takeoff. And it makes a difference in how much air is being delivered to a space. Classic example, okay, you have a customer who calls and says, my master bedroom just is always feeling warm. Okay, so you go in, you take temperatures, and sure enough, you confirm it is warm. You go take a static pressure at the air handler. You go take a static pressure at the takeoff, and you realize that there's no way there's enough airflow. Okay, you have very low static pressures at that takeoff. What do you do about it? You have to figure out a way to reduce friction or increase velocity. Okay? And that's doable with duct design and dampers. Okay, let's move on. Air disturbances cause dynamic loss. So anytime there's a damper, anytime there's a bend in ductwork, you'll see the blue arrows on this slide is airflow. Anytime we have something that disturbs the straight line flow of air, okay, air likes moving in a straight line. If you don't have air moving in a straight line and don't help it maintain a straight line, okay, you will have what we call a dynamic loss. Anytime the airflow has to move around things, there is loss. Okay? Changing duct sizes, okay, can cause a change in air velocity. Now, sometimes we do this on purpose. Okay, if I maintain air velocity and reduce the size of pressure, the ductwork, I can actually increase my static pressure. Okay, so playing with the size of ductwork as my main run goes from one side to another, I can change the velocity pressure, I can change the static pressure, and I can change the total pressure. Now, when we take a look at this chart here, okay, at point A, I have the maximum static pressure and I have the maximum velocity pressure. We go from B to C. Okay, I'm decreasing the size of the duct. So I'm going to decrease my static pressure because I'm going to have a pressure drop because I'm restricting airflow, but I'm going to increase my velocity pressure. I can speed up air by decreasing the size of the ductwork. From C to D, I'm going to lose some static pressure just because of the friction against the side of the ductwork. That's pressure loss. Now, when I go from D to E, I'm increasing the duct size, okay? So I am going to again lose velocity pressure because when I increase the size of ductwork with the same amount of air, it now moves slower. E to F, I'm going to lose static pressure because anytime I put something in the flow of air like a coil, I'm going to have a dynamic pressure change. Okay, I'm going to have pressure loss. And then as we go from F to G, I'm going to decrease static pressure because it's at the end of the run and it's blowing into a wide open area. Okay, so as you can see, every fitting and everything you put into a piece of ductwork makes a difference in the pressures, okay, that change air velocity, change quantity, okay, because remember, velocity is part of the quantity of air being delivered.